I am Akshay, and I have recently joined as a postdoc here and working with Anirban. Today, I would like to talk about the topology of random geometric complexes in high dimensions. So basically, the aim is just to give the problems, statements of problems on which I am working with with basic results which I have so far. And so let me start with some introduction. So there is an emerging research area known as random topology. It comprises of the theoretical results. Okay. So this random topology can be thought as a collection of all theoretical results that characterize the asymptotic behavior of topological properties of random objects. And one aspect of this area is the study of random geometric complexes and their topological properties such as homology or Beatty numbers. And if I tell you more specifically, it is like this. One is interested in the asymptotic thresholds for non-vanishing and vanishing of each homology groups of these complexes. And where the homology groups do not vanish, we would like to know the asymptotic behavior of Beatty numbers as well. So this, the motivation, of course, they have a mathematical value, but their motivation also comes from a applications point of view, such as topological data analysis, where these kind of studies provide a probabilistic null hypothesis to compare with the topological statistics of the point cloud data. So what happens in usual random topology is you have random points, you construct some random object and study its topological properties as the number of points goes to infinity. That is the usual random topology. But if you look at this, in these studies, what is happening? The data points, the number of features in the data point, which represents the dimension in which the data point lives, is fixed, while the number of observations is going to infinity. And but nowadays, our data sets are high dimensional. That means the number of features can be comparable to the number of observations. And the aim of this project is to study the similar type of questions in this high dimensional setting. I will explain more what is high dimensional setting, but before that, let me give you some definitions of the keywords what we have used in the first two slides. So first is geometric complexes. And so our focus is on two typical geometric complexes, namely check and rifts. And so suppose you have a finite set of points in RD, and both complexes are just the collection of the subsets of this finite point set. So in Rifts complex, you collect all the subsets of Xn which satisfies this geometrical constraint. That is, you take any subset and draw the ball of radius r around that point and look at the pairwise intersection. So if the pairwise intersection is non-empty, then you put this in the Rifts complex. And if the overall intersection is non-empty, then you collect it in another collection that is known as check complex. Clearly, this check complex is a subset of Rifts complex. And any element belonging to any of these complex is called a K-simplex if its cardinality is K plus 1. Now, these geometric complexes are not random. To make these random, we take this finite point set to be random. So how we will do that? In this our setting, we will use a homogeneous Poisson point process. What is this? It is just a random collection of points in RD which satisfies these two properties. The first property says just take any bounded Borel set and look at the number of points lying in that set. It follows a Poisson distribution with parameter n, and this is the Lebesgue volume of B. So this n is called the intensity. And since n is a constant here, this point process is called a homogeneous one. And for disjoint bounded Borel sets, the second condition is it has to satisfy is that the random variables PV1, PV2 up to PVK are independent. And that's why we are using Poisson point process, because it gives us this nice independence property. Now we have randomness. We put in geometric complexes, we get random geometric complexes. If you restrict these random geometric complexes to just vertices and edges, so sorry, I didn't tell that this 0 simplex is just are the vertices, 1 simplex are the edges, and for 2 simplex you can think of it as a triangle, and so on. So if you restrict it just to edges and vertices, you will get random geometric graphs, for which we have a very large literature due to Penrose and others. And from there we know that there are basically 3 different limiting regimes in which the topological behavior is significantly different of these geometric graphs. And so we have these 3: sparse, thermodynamic, and dense. This is the typo, this is not lambda, this is n. So this is the, basically this quantity is the expected number of points in a ball of radius Rn. And if it goes to 0, you are in a sparse regime where most of the points are isolated. Then you move into thermodynamic regime where it converges to a positive constant. Here you will get a giant component, and then you move into the dense regime. And in dense regime, it's like connectivity is happening. Everything is connected. That's why it's called dense. So now we have the limiting regimes, and the other quantity, the topological quantity which we want to study is Betti numbers. I will not describe them properly, but we can have some intuition for them. So we have kth Betti numbers for every natural number k, including 0. And zeroth Betti number is basically counts the number of connected components in the complex or a graph. For other case, it counts the number of k-dimensional holes. And okay, so this might not have a good intuition, but in case of check complex, we can think of Betti numbers. For example, you look at x4, x5, x6, the triangle, and this is hollow triangle because the overall intersection is empty. Therefore, it gives you one-dimensional hole. That is, Betti 1 is 1, and Betti 0 is also 1 because this check complex is connected. So we have all the mathematical the mathematical things which we need. So now we will describe the high dimensional setting. So what is happening in high dimensional setting? We are taking the dimension of the space also to infinity, not only the number of points or nd. So we will consider this setting. We will consider a unit hypercube and equipped with the toroidal metric. So we are using this toroidal metric just because to avoid the boundary effects. And then we consider a homogeneous Poisson point process with intensity and d. So now everything will depend on d as the dimension is varying. And similar to the case of usual random topology where we have 3 different limiting regimes, here we also have, which is given by nd rd power d omega d. This omega d is the volume of a unit cube. And in this setting, throughout rd is going to 0 and nd is going to infinity as d tends to infinity. And the aim of this project is to study the systematically and comprehensively the behavior of Betti numbers of both complexes in all the regions. So far, whatever results we have, these are we have in the fixed dimension. So some heuristics in this work. The first one is we have local weak convergence of nearest neighbor graphs in a Poisson point process that tells that the random geometric graph will look like a tree in high dimensions. And furthermore, these random geometric graphs in high dimensions should behave like Addo-Shreni graphs, as there are several references for that, but in different settings. So we would like to use these heuristics or in the context of random topology in the high dimension setting. There are some challenges. One of this is that the constants which depend on the dimension are not now constants, and therefore we have to study their asymptotic behavior as well. And there is another challenge, which is lack of ergodic theorems. These ergodic theorems in fixed dimensions helps one to say the say the existence of the limit in the asymptotic cases, but here we do not have. So a deliberate analysis is required to overcome these obstacles. So we have started some basic calculations, and this is our ongoing work with Yogesh. He's associate professor at ISI Bangalore. So in this business, what people do is we first calculate the number of simplex counts, and from there we estimate the behavior of Beatty numbers. So similarly, we did something here. We calculate the expectation of simplex counts, and we have a nice expression, nd 1 over k plus 1 factorial nd lambda d power k jkd. Now in fixed dimensions, this jkd is just a constant, so one need not to be worry and one can throw it away. But in high dimension setting, we need to study what happens to this jkd as d goes to infinity. So of course, this jkd has a nice expression in the integral form. I have written for only k equals to 2. So we study the asymptotic behavior of a small jkd, and in this way. So first we show that the ratio goes to 0, jk plus 1 comma d divided by jkd, and another we showed that the ratio of ratios also goes to 0. Okay, so this result is not entirely proved yet. There is some technical thing that is the obstacle, but I have a very good heuristic because of which it holds. So once we have this, we get some conclusions about simplex counts in the 3 different regimes. So in sparse regime, as I said, in sparse regime is where most of the points are isolated. So here it is happening the same. So this is similar to the case of fixed dimensions. But once you move into the thermodynamic regime, what is happening here is the edges are dominating our all other simplexes. That does not happen in the fixed dimensions, and so in the fixed dimensions, all k simplex counts are of the same order, and this gives this also matches with the heuristic that it graph looks like a tree in high dimensions. So since only the edges are dominating, we will not see higher simplexes. And in dense regime, now since we have this
you have 2 minutes.
Okay, good. So in dense regime, when we have this ratio of ratios going to 0, as a consequence, we get that jkd divided by jk plus 1d is dominating by jk minus 1d divided by jkd. Therefore, we can choose lambda d such that this is satisfied. So how to? Okay, this is satisfied. Once we have this, so we can choose lambda d such that it is satisfied, and in that scenario, we have this result. So here also one of the only when L equals to K, then only those K simplexes are dominating are here, otherwise all other goes to 0. So this kind of stuff also does not happen in fixed dimensions. So why we, as I told you that we start with the simplex counts due to this inequality. So once we have the results for simplex counts, we can calculate, we can have some results for the Beatty numbers as well. In the thermodynamic regimes, when you divide the expectation of Beatty numbers by ND, only for k equals to 0 and k equals to 1, you will get some positive limit, otherwise it goes to 0. This is also very different from the case of fixed dimensions, where every Beatty number is of order ND, means expectation of Beatty k divided by n goes to some finite limit in the case of fixed dimensions. And similarly, we obtain a result of in dense regime. This result is analogous to the result for the simplex counts. So just you have to use this inequality to obtain this result. So these are of the some results, and this is some plan okay. So first, I would like to make more stronger statements in this business, that is like convergence in probability and some obtained distribution results. And we also studied one other thing, that is the spectral gaps of high dimensional random geometric graphs. This is the work I studied with now Anirban and Yogesh, and maybe we'll talk about this at some other point of time. Thank you.
Thank you, Akshay. We have time for one question.
Some regime was called thermodynamic regime. So
Don't ask me why it is called thermodynamic.
Yeah, I mean, does it have any connections? With...
Okay, I do not know because so what I've read, the word comes from physics literature, but I do not know what is why it is called thermodynamic. That's what you are asking? Yeah, sorry, I don't know.
Okay, let us all thank Akshay for his beautiful talk.